Let's begin by briefly talking about something which is common knowledge. In Java, variables are only accessible within the region it is created. This region is called the scope of this variable. Let's spend some time gazing at this class called HTTP caller on the screen. You will see the various variables that are used in the class. I have also noted the scopes of these as well. The scope of member variable call name is restricted to within the class itself. The scope of parameter secs seconds is restricted within the method called makeCall. Variables URI and request both are restricted within the try block. So that's the block scope. Variable exp is also restricted to the catch block. Now the interesting variable is client. That's declared as public and static, which means it can be accessed from anywhere in the JVM by any thread, simply by using the syntax http://caller.client. It's almost like a global variable. Now what's missing in the above scopes is a scope which is specific to a particular thread. We want to be able to define a variable which can be visible to the entire call stack for a thread, but not to other threads. In other words, it should be global, but global only for a thread. Now that's exactly what thread locals are. Let's refresh our knowledge of thread locals. Anyone who has been programming in Java for a long time knows that thread locals exist, but we often hesitate to use it. In fact, we often tend to use it indirectly through frameworks. For example, in Spring Security, the user who is accessing the enterprise application is stored in a thread local variable behind the scenes. And this implementation detail is hidden from the programmer. So how do we declare a thread local variable? On the screen you see a thread local variable called user. In most cases, a thread local variable would be defined as public static so that it can be accessed from anywhere. Even though it looks like a global variable, it operates a bit differently. You can set the variable using the set method, and you can get the variable using the get method. Now this is deceptively simple. The big difference here is that it is set for a particular thread. So if thread 1 sets a value of Bob, and at a later point of time in a completely different method, when thread 1 calls get, it will return Bob. However, if thread 2 calls get, it will not return Bob. It will return whatever the value was set for thread 2. Note here that the variable user itself has a global scope, but the value you store in it has a thread local scope. When the set method is called on the user object, it internally associates the value with the calling thread. When the get method is called on the variable, it simply returns the value associated with the calling thread. In fact, each thread is associated with a map of thread locals, which stores the association between the thread local and the value. The thread local class has a method called remove, which removes the value which is associated with that thread local for that particular thread. Again, it does not affect the value associated with a different thread. Now there is also a variation of the declaration of thread locals, where we can pass a supplier. In this case, whenever the get method is called and no value is associated with a thread, then the supplier method will be called. Instead of null, you would get the value returned by the supplier. That will get associated with the variable and put in the thread local map. So in the example on the screen, when any thread calls the get method, it will return the anonymous user object and not null. Note again that you will get different user objects for different threads, since that is what we have specified. Typically, the value you store in the thread local variable is thread safe since only one thread will ever operate on it. You won't need to synchronize methods. Now, this is true only if the value object is not passed to a different thread in some other way, and that will make it thread unsafe. Now, enough of theory. Let's jump to some examples which will make this crystal clear. Here's a simple class called thread local simple play. Let's go through this code. Here we declare a thread local called user. This user stores a value object of type user. Here's how user looks. Simply a pojo. It just holds an ID, and much of the code related to constructor, getter or setter is not shown. We have a main method which will simply do some gets and sets on the thread local user and then call a handle user method. The handle user method in turn simply delegates the handling of the user to a separate class called user handler. Now that's what you see on the screen, the user handler class with the handle method. Now the handle method simply gets the value associated with the thread local user and displays it. It simply accesses the thread local object as thread local simple play dot user, because as we mentioned before, the user variable itself must be accessible to the code which calls the get and also the set. Much of the other code in the handle method is not important and is missing. Here we have the print method just for printing log messages. It will also print the thread name along with the message, and this would be useful for debugging. So let's go over the execution of the code and see what happens during the print messages. Over here, what gets printed over here? Null. Why? Because nothing has been stored in the user local variable. So the first time when you do a get, it simply returns null, which is empty. Over here you will see that the thread local variable is being set with an anonymous user. That's simply called using new user, and you pass the ID. So at that point, what is the association that is made? For the main thread, user thread local is associated with anonymous because main thread is the calling thread. Now over here, when we print it, what gets printed? Anonymous. Now inside the handle method, we call the get method, which will get the user associated with the main thread. Why the main thread? Again, it's the main thread which is calling get. It should print anonymous. So overall, the output of this method will look as follows. All running in one thread, the main thread. So basically, this code demonstrated the fact that the handle method of the user handler was able to access a thread local variable called user. We avoided passing the user as a parameter to this method, but it was able to simply access the thread local variable. But this example was straightforward and not very exciting. Let's get another thread in the mix and see yet another example. Now here you see a class called thread local play. Again, a thread local variable called user is created as public static final. So this way the user can be accessed from anywhere in the code. So what gets printed out here? It prints null because the user is not set. So it will always return null. There's no initializer specified. The code goes ahead and sets the user main for the main thread. So there's a user called main, which we are setting for this main thread. And then what gets printed out here? It prints user main because the get will return user main. Now at this point, things get a bit interesting. The code starts a new virtual thread and passes a lambda which is going to be executed in a separate thread. I have named this thread bob-thread. So at this point, you have two threads running in parallel, the main thread and the bob thread. Note here that this line gets executed by thread bob thread and not the main thread. Get will return empty or null because nothing was set earlier in the bob thread. The set which is called by the main thread over here is not seen by the bob thread over here. This is as expected. Let's go ahead and set it in bob thread. Now when set is called on the bob thread, thread local user gets associated with bob, user bob. Note, the value associated with the main thread has not been affected when we do this. So over here, at this point, it will print bob. So all this time when bob thread was running happily, our main thread was waiting on the join right over here. Once the bob thread ends, the main thread will wake up from the join call. The next statement it's going to do is the print. What will it print here? The get method over here will get the user associated with the main thread, which is still user main. So that's what it's going to print, user main. So finally, the output of the above program will be as shown. I have numbered the print lines on the left of the code, and the corresponding output in the run output window is shown on the right bottom. You can see lines 2 and 5 on the output and see that the user is exactly the same user. Nothing which happened in the bob thread affected the main thread. It still got the exact same user, user main, exact same object. Now what if we call an initializer to create the thread local? Let's do that. Here we have a class called thread local initializer play. The only change that is made is out here during the initialization of thread local. Now the initializer supplies a value for the user when the get method is called. In the supplier, we are simply going to return a new user with ID anonymous. Now when we run this, what do we expect? Let's see the output for this. Again, I have numbered the code on the left from 1 to 5, and the output is seen at the bottom right. You will see lines 1 and 3, instead of null, what's being printed is user anonymous. So when there was nothing set for the thread local variable, the thread local variable will automatically get what was supplied as the initial value during initialization. Now this gives us a good understanding of thread locals. It can be a bit tricky if you are not used to it. But if you like diagrams like I do, here's a nice way to imagine thread locals. What you see on the screen are two virtual threads, thread 1 and thread 2. By the way, it can just as easily be platform threads. Each thread keeps a copy of a map of thread locals, each map specific to their thread. The map associates a unique thread local key which is internally generated to the actual value. On the screen, what we see are three thread local variables: user, request, and transaction. Each thread would be pointing to its own copy of the value objects. As mentioned before, the keys are uniquely generated by the JVM. So in our case, if thread 1 calls the get method on thread local user, it will simply go to the thread local map of thread 1 and return the user object associated with that thread. And as you can see, the map is pointing to different copies of the user object, and that makes the user object thread safe. Now, unless of course this user object is passed to a different thread, which would make it thread unsafe. Now, this concludes the discussion on thread locals. The thread local variables have a scope within the thread. One good thing about thread locals is that if you create a child thread, the thread locals from the parent are not automatically carried over to the child. The child may never access the parent thread locals, and so there is no point in making that visible to the child by default. This design is on purpose so that we get good performance and also control the memory inside the JVM. But this advantage is also a disadvantage. There are times when we want the child thread to have visibility to the parent's thread local. Let's say you store the user and its security attributes in a thread local variable, and you spawn a new virtual thread or platform thread. The child thread may like to know the user information and these security attributes. That seems reasonable. So in order to satisfy this requirement, Java provides us with a class called Inheritable Thread Local. This class extends from thread local class, does everything that the thread local does, with the added ability that when a child thread gets created, then the inheritable thread local gets copied over to the child. As a programmer, the inheritable thread local class can be used almost exactly like the thread local class. Here you see the declaration of the inheritable thread local variable. This time we are using the class called inheritable thread local instead of thread local. You can use the get and the set methods on these thread local objects almost exactly the same, no change over here. And then use the remove when not needed. These methods work exactly the same. The only difference is that when a child thread gets created, the inheritable thread local values get copied over to the child. But how exactly is this copying done? By default, the child value will be identical to the parent value, meaning that the child and the parent values would be pointing to the exact same object. This may be what you want, or this may not be what you want, because this has synchronization implications. Let's look at a concrete example of how this works. Here's a class called Inheritable Thread Local Play. Right over here, we declare the inheritable thread local variable. Over here, we set the user, and when we print it, we get the user main. No difference here. This is as expected. The code goes ahead and starts a new virtual thread and passes a lambda as before, and we go ahead and set the thread name within the lambda. Everything within the lambda is being executed in a new thread called Bob thread. So what gets printed out here? Since user is an inheritable thread local, the get method will get user main and not null. Because when Bob thread got created, user variable got copied over to Bob thread from the main thread. The JVM did that for us. Now at this point, I'm going to set the ID of the user to Bobby from main. Note that I'm changing the user object itself and not setting the user thread local variable. So what gets printed in the next line is user Bobby. That's as expected. Now let's switch over to the main thread. Once Bob thread terminates, the main thread, which was waiting on the join, now wakes up, and what do you think it prints in the next line? It's going to print Bobby. The reason it prints Bobby in the main thread is because the Bob thread changed the exact same user object that both main thread and Bob thread were pointing to. So the output of the program will look as follows. You can see the line number 3 where Bob thread prints user main because it got copied over from the main thread. You can also see line 5 where the main thread printed user Bobby. Comparing 4 and 5, you see that the inheritable thread local variable user is pointing to the exact same user object. You can see that by the user reference. The implication of this is that the user class must be written in a thread-safe manner. Its methods need to be appropriately synchronized. Let's get some more insight into inheritable thread locals. Java's thread class keeps a copy of two maps, the regular thread local map, but also an inheritable thread local map. Values of the inheritable thread locals go into the inheritable thread local map, whereas the values of the regular thread locals go into the thread local map. Now here you see three inheritable thread local variables in the thread map. Thread 1 also has a thread local map that is separate, and I'm not showing it. Now you can also think about thread 1 as the main thread from the previous lecture. At some point when a child thread gets created, right here it's spawning a new child thread, what happens? During the creation of the child thread, one of the things that is done is a copy of the inheritable thread map from the parent is used to create the inheritable thread map of the child. Right here, the map gets created. And as you can see, the default implementation of the user, which is an inheritable thread local, is just copying the value to the child, which means both of them are pointing to the same user object. Now you can think about this child thread as Bob thread from the previous lecture. By default, all the values would be copied as it is. So you see the user reference pointing back to the same user object. This is exactly why when Bob thread changed the user object, it got reflected in the main thread as well. But what if you do not want the default implementation of child value? Well, we are in luck. We can change the default implementation by overriding the method called child value. It takes the parent value and then we can return whatever we want to set as child value. What you see on the screen is a creation of the inheritable thread local object, but I am providing an implementation of child value method where a new user object is created from the parent and returned. Also, I overrode the method initial value, which will return anonymous user. Now let's see in the diagram what happens if we create an inheritable thread local in this way. You see thread 1 with inheritable thread local map. When the child thread gets created, what happens? The inheritable thread local map gets created from the parent, but the child value method is called on each inheritable thread local variable to get the child value. So what we see now is that the user variable of child is pointing to a brand new Java object and not the same object of the parent. This is the result of our defining the child value method while creating the inheritable thread local variable. So essentially now user becomes a thread safe class again. But the implication of this is that the child cannot propagate any changes back to the parent via the user object. So choose your design very carefully depending on your requirements. What happens if we run our example with this new way of creating the inheritable thread local object? Now here's the same inheritable thread local play class, but with the new way of constructing the object. It has a default value which returns an anonymous, and it also has a child value which returns a new copy of the user object. The output would be the following. You can go through this output and match with the print statements, but essentially if you look at line 1, it prints anonymous and not null. And also, line 4 and line 5 point to different user objects. Whatever we did in the Bob thread did not affect the main. Now, this concludes our discussion of inheritable thread local variables. Thread local variables remain a viable way to design your systems and work with both platform as well as virtual threads. Let me begin by saying that thread locals have been in the Java ecosystem since the 1990s, and it remains a valid way to set and access data within a thread. But we should also be aware of the downsides of using thread locals. The first problem with thread locals is that it has unconstrained mutability. By mutability, I mean the ability to change the thread local. Set method on the thread local can be called anywhere in the thread, and get method can also be called anywhere in the thread. That is, anywhere there is visibility of that thread local. Remember, by mutability, I mean the mutability of the thread local and not the mutability of the value set for that thread local. They are two different things. To clarify this point, if you look at one of the earlier diagrams on the right, the thread local for user can be changed by using the set method right here. This is the mutation we are referring to. This is independent of the change to the user object itself, which is here. I can set the ID for the user, which is basically mutating the user object itself. That is not the mutation that we are referring to. So basically, even though Java allows you to set thread locals from anywhere in the thread, a good practice to design it is to be able to set at only a single location and then use it at more than one place. That's a pragmatic approach, and that's what we have seen more than 90% of the time developers do. Also, if you don't need the value to be mutable, then you can simply use a Java record, which is by definition immutable. So in this example, user could be a Java record instead of a Java class. The second problem with thread locals is the unbounded lifetime of the thread local variable. Thread locals remain in the thread local map until the thread dies or until it is removed explicitly using the remove method. We have seen this before. So if the developer sets the thread local variable but forgets to remove it, then we have a potential memory leak in our hands. This is not a problem with virtual threads as much, because virtual threads are supposed to be used and discarded. They are never pooled. If you find yourself trying to pool virtual threads, then you are doing something terribly wrong. In other words, virtual threads make the case for thread locals actually stronger because it doesn't have the memory problems which it has in platform threads. So let's say you're using a thread pool, obviously with the platform threads. If you look at an individual thread inside the pool, it's running different tasks continuously. You see in the diagram task 1 and task 2 submitted by other threads. Task 1 sets a thread local right over here. What happens when the developer forgets to call remove at the end of the task 1? The thread local value would not be garbage collected because the reference to that is still in the thread local map for that thread. And the thread is not going to die anytime soon. The entry in the thread local map will also not be removed. Worse still, the thread will start running some other task soon, which now has access to the thread local created from task 1. Now, this scenario could create some very hard to debug problems and possibly some security issues too. As developers, we should be always removing the thread locals from the map, possibly in the finally block. The next problem is really to do with inheritance of thread locals. Basically, the inheritable thread local objects. We already mentioned that when a child thread is created, the inheritable thread local map is copied over to the child. The reason the JVM needs to do this is that the child should be able to set its own value. This is a reasonable implementation given the constraints. But consider what happens if we are using a lot of virtual threads. A developer can create tens of thousands of virtual threads in the JVM. We have seen in structured concurrency, we can create these child threads, and these child threads can in turn spawn other child threads. If we copy the map as we do for all of these threads, we have a potential memory problem in our hands. Also, there is a performance problem because of the copying of these maps.